All right. So the next rule we have to get into is the sum and difference rule. All right. And I'll write it out, and then we'll prove it after I write it out. All right. The sum and difference rule tells us. So sum and difference. All right. Diff. Tells us that if we want to take the derivative of the sum of two functions, all right, we see these kind of functions all the time. All right. Like y equals x squared plus x is a function that is the sum of two different functions, x squared and x. All right. So this rule would tell us how to take the derivative of these kinds of functions. All right. And it tells us that the derivative of the sum of two functions is just the derivative of the first function plus the derivative of the second function. All right. And that might seem pretty self-explanatory, but I still want to explain it because when we get into the product rule in just a second, the product rule, the derivative of the product of two functions is not the product of their derivatives. So even though this might look like it makes sense, then if this made sense, then it would seem like the product rule would be the product of the two derivatives, but it's not. So I want to explain why this is true, because if we just say, well, it makes sense, then that logic doesn't really work for the product rule, which is not what we would expect it to be. Does that make sense?
Yep.
Cool. So if I have a function that is just the sum of two other functions, I like to use x squared plus x, all right, and I graph it. All I'm doing is I'm taking the two individual functions, x squared and y equals x, and adding them together at each x coordinate to get the new height of our new function. So for example, if I wanted to graph this new function, I would take whatever the heights of these two functions are at each x coordinate and add them together to get our new x coordinate. All right. And forgive me for my poor drawing. But do you see how this function, all you're doing is you're just taking the heights of the other two functions and adding them together to get the new function at each x coordinate?
Yeah.
All right. So I could say if we wanted to take the derivative of this function, we'll do the following thing. Well, I'll outline the way I'm going to do it in just a second, so that when I do it, it isn't foreign to you. But remember how yesterday or on Friday we said that all a derivative is dy over dx, a tiny change in y divided by a tiny change in x. Because as we zoom in close to a function, it's going to look like a line. So we just find the derivative by taking the tiny change in y and dividing it by the tiny change in x. Would you agree?
Yeah.
Cool. So this is an equation, and we can treat it as such. So if we multiply both sides by dx, we would get the tiny change in y is equal to our derivative times dx, just by multiplying both sides by the same thing. You say that's valid?
Yep.
Cool. So let's go back to our original function. All right. You'll notice that if I want to find the tiny change to our function dy when y equals x squared plus x, the tiny change to this function, because this function is just adding this to this, would you agree that the tiny change, will say d x squared plus x, the tiny change to this function, is just equal to whatever our tiny change in x squared is plus whatever our tiny change in x is. Because we get the heights of this function by taking whatever the height of this function is and adding it to whatever the height of this function is. So if we increase our x coordinate by some tiny value, the change in our y coordinate is whatever the change in this y coordinate is plus whatever the change in this y coordinate is. Does that make sense?
That makes sense to me.
Cool, Ryan? All right, I'll assume we're all good. So I could write that d x squared plus x equals d x squared plus dx. Tiny change in this function is equal to whatever the tiny change to this is plus whatever the tiny change to this is, because this function is just this function plus this function. Does that make sense?
Yeah.
Cool. And remember how I said that we could rewrite the derivative as f prime of x equals dy over dx. So then I could say, well, if this is true, then I multiply both sides by dx, and I get f prime of x equals, f prime of x times dx equals dy.
Yeah.
All right. Cool. All right. So I could take this, and I'll bring it to the next slide. Dx squared plus x equals dx squared plus dx, right? And because we said dy equals f prime of x times dx, all right, I could write dx squared as f prime of x, the derivative of x squared, times dx. And I'll write here, let's say that f prime of x is when f of x is x squared, and g prime of x is for when g of x is equal to x. All right. So I could rewrite, if we say that f prime of x is the derivative of x squared, then the tiny change to x squared, which is the same thing as saying dy, is the derivative of x squared, f prime of x, times dx from the equation we had on the last slide. Does that make sense?
Yeah, I think so.
Cool. If you say you think so, is there anything that might be worth like saying one more time or explaining again, or?
I think I get it. I think I'm just taking not great notes. I'm like a little all over the place, but I think I get it like in my head.
Okay, if you need me to backtrack so we can get your notes back down, just let me know. Okay.
Okay.
And you don't have to write down the notes for these proofs as long as you understand why they work.
Yeah.
Because these videos will be available to you guys as well if you want to rewatch them.
Yeah, I was just thinking that.
Yeah. So all I really care is that you understand that they're valid, and then you're good to go. That's my opinion. I think if you understand that something is valid, then you can use it as much as you want.
Yeah, I agree. That makes sense.
Right. So similar here, we have a dx, which dx, the tiny change to x, is just the derivative of x, all right, times dx. Because the tiny change to our function dy equals the derivative of that function times dx. That's all we're doing. We're rewriting the dy, the change to the function, as the derivative times dx, because we said it's a valid thing to do in the last slide. Cool?
Yeah.
Cool. All right, so finally, we're almost done. Dx squared plus x equals f prime of x dx plus g prime of x dx, right?
Can I just take a sec to write that down?
Of course.
Perfect, thank you.
Cool. Now we have an equation. So it's valid if I just divide both sides by dx, right? If I do the same thing to each side, it's still valid. If I divide this by dx, well, then this dx goes away, and this dx goes away. All right? So here we have a tiny change to our function x squared plus x divided by a tiny change in our input. What is this by definition?
Oh, it's just like d over dx of x. Like it's just the derivative of the function.
Perfect. All right. So we have an equation that tells us, well, the derivative of this is equal to the derivative of x squared plus the derivative of x. Right? So we just showed mathematically how the derivative of this plus this is equal to the derivative of this plus the derivative of this. And although we used a concrete example here, we actually used a real function. You could do the same thing and just generalize the two functions and do the same process, and you get the same thing. If you add two functions together, the derivative of their sum is just the sum of their derivatives. That's a mouthful, but that's what this is saying.
That makes sense. I'm with that.
Cool. And additionally, you could do the exact same process, so I won't do it again, to show that the derivative of f of x, a function minus another function, is the derivative of the first function minus the derivative of the second function. You would do the exact same proof that we did here. So I won't do it again, but it's the same logic and same process. We cool?
Yeah.
All right. The next rule we have to cover is the product rule. And do you guys like visual representations? Because there's a really cool visual representation for the product rule that won't take too long.
That sounds great.
Cool. All right. So the product rule. The product rule tells us that the derivative of a function multiplied by another function equals, and it's hard. You can write this down. I'd recommend you write it down first, so then we can prove it later. Is the derivative of the first function times just the second function on its own, plus the derivative of the second function times just the first function on its own. And if it seems complicated, we're gonna explain it. Don't worry. So I would write it down so we have the rule written down, and then we'll prove it in just a minute.
Okay.
All right. How are we feeling?
I'm good.
Good.
Ryan, how you doing? You there, Ryan?
Ryan, you all good?
Yeah, I meant to mute by accidentally alt-tabbed. Yeah, I'm good.
You're no good. I mean, you're good. You're good. You're good. That's what I meant to say. All right. So here, I'm going to do a visual representation of this proof. Let's say I had a rectangle that one side length was f of x. The side length, one side length was given by the function f of x. And the other side length was given by the function g of x. All right. We have a rectangle whose one side is given by f of x and the other side is given by g of x. So depending on what x is, f of x will tell us what the length of our rectangle is. And it's different depending on what the value of x is. For example, if f of x was x squared, if x equals 2, then this side length would be 4. So we're making a rectangle that has side lengths that are functions that, obviously will produce different side lengths depending on what the value of our function is. But you kind of get what I'm doing here?
Yeah.
Cool. So tell me, what would the area of this rectangle be?
It would be f of x times g of x.
Exactly. And what are we trying to find? The product rule, right? So this seems like a pretty good start. All right. So naturally, when we're trying to find derivatives, we're trying to ask what happens to our function as we increase our input by some tiny dx. Wouldn't you agree that's what we're trying to figure out when we do derivatives? What happens to our function as we increase our input just a little bit?
Yeah.
The derivative tells us how much it increases or decreases. So asking the question what happens as we nudge our x value up a little bit will naturally give us information about the derivative. All right. And wouldn't you agree, if we nudged our x coordinate up just a tiny bit, all right, then the length of the rectangle would increase just a tiny bit, all right?
Yeah.
Cool. And remember our equation that a tiny change to a function is equal to the derivative of that function times dx. This is a really important equation to remember. Because if we divided both sides by dx, we'd get a tiny change to f of x divided by a tiny change in x is equal to the derivative of that function, which by definition is true. So all we did is took that definition and multiplied both sides by dx, and we got this.
Yeah.
All right. So this tells us that the tiny change to a function value is equal to the derivative times whatever our tiny change in x is. All right.
Yeah.
So wouldn't you agree that the tiny change to the side length, because the side length is represented by f of x, would be df of x? It'd be a tiny change to f of x, which equals the derivative of f times dx. Would you agree?
Wait, say it again?
So if we increase our input by a very tiny value, right, this side length is going to change by a very small output, df of x.
Yeah.
Cool. And remember, df, the change in the output of our function is the derivative of the function times whatever the change in our x value was. So if we change our x value a little bit, then the resulting change in our function, which is the additional side length we get here, is f prime of x times dx because of this equation.
Okay, yeah, that makes sense to me.
Cool. Additionally, we do the same thing down here. We get, if we increase our input by some tiny dx, that means that this side length increases by g prime of x times dx with the same logic. Do you see that?
Yeah, can I just take a sec to write this down?
Of course, of course. And if it's not making sense, we can backtrack, but...
Okay, I think I'm all good.
Cool. So, and the last new bit of area we get is this little part right here. All right. When we increase the side length of our rectangle, you'd agree that we get that our new rectangle would be this, right?
Yeah.
So the new area is this rectangle, and this thing right here.
Yep.
Cool. So here I'm running out of space. I'll try and do this on the side, and if it's getting too crammed, I'll do it somewhere else. So if the function f of x times g of x is the area of the rectangle, then would you agree that the change in this function, d f of x times g of x, equals whatever the new area is? Because that's the change in our area. So it's the change in our function.
Yeah.
Cool. So this is a rectangle, and we know that one side length is f prime of x dx. So we get f prime of x dx. Times, and the other side length, you can see this side length is g of x. So that's one rectangle, right? That's this rectangle.
Yeah.
Cool. This rectangle, we have as a side length here of g prime of x dx. And a side length here of f of x. You see how they're the same length?
Yep.
Cool. And so we've got the area of this, and the last thing we have to do is do the area of this. This length, you can see up here, is just f prime of x dx. And this length down here is g prime of x dx. So when you multiply them together, you'll get g prime of x, f prime of x, times dx squared. Because when you multiply this by this, that's what you get. Cool?
Yeah, wait, let me just write that down real quick. So the first part, like f prime x dx times gx is the rectangle, like with the extension on the right.
Yep, this is
so it's that part, but not the extension vertically.
But not this one, you mean?
Yeah, right?
Yeah, so the first part is the area of this rectangle.
Yeah.
Yep. The second one is the area of this rectangle.
Yeah. Okay.
And the third one is the area of this rectangle. And we said that that's equal to the change in our function because our function is the area of the rectangle. So the change in our area is the same thing as the change in our function. That's why.
I see where I was confused. I get it now.
Cool. All right, so we got this.
Sorry, and then wait. So what's real quick? What was the equation for finding the little square? It was g prime of x dx plus f prime.
It was g. You take so the length here is g prime of x dx, and the length here is f prime of x dx. You see how they're the same. So if you want to find the area of the square, you have to multiply them together. And if you multiply these two things together, you get this. G prime of x times f f prime of x times there's 2 dx's, so we get dx squared.
Perfect.
Cool. All right, so let's rewrite what we have. Oh, wrong thing. So we just showed that this is true. There's supposed to be a dx here. I drew it very poorly. Uh-oh. All right, so this is just the equation from the last slide, right? Let's divide both sides by dx. When we divide this by dx, we get df of x times g of x over dx equals, and if we divide this side by dx, if we divide this term by dx, this dx goes away. We get f prime of x, g of x, plus g prime of x, f of x, because when you divide this term by dx, this dx goes away, plus f prime of x, g prime of x times dx, because when you divide dx squared by dx, you just get 1 dx, right?
Yeah.
Last thing, when we're doing derivatives, right, what do we say about the tiny change in our output? Is it big or small when we're calculating derivatives?
It's really small.
Exactly. So what can I say about this dx term? It's really small, right?
Yeah.
So in other words, I could say it's getting closer and closer to 0.
Yeah.
So then what can I say about this term as a whole? Do I care about it?
Not really, no.
Exactly. Because when we're doing calculus, we're actually looking at a tiny change in our input as that input gets closer to 0. Remember from our limits, we're evaluating the distance between the point getting closer to 0.
Yeah.
So this is the same thing. The tiny change in our output is getting closer to 0. So this entire term becomes 0 and we can ignore it.
Okay, cool.
Cool. So let's break this down. What is this side saying? A tiny change to the product of these things divided by a tiny change in x. What does this mean?
That's the derivative of the function?
Exactly. So then we just showed that the derivative of the product of two functions is equal to this. And that's the product rule. Money. Yes, money indeed.
Sorry, just give me 1 sec to write some stuff down.
Cool. Do you guys like that kind of proof, or we do visual proofs? Do you guys like those?
Yeah, I really like that.
Cool. And if that was a little confusing, I can send you a link to 3 Blue 1 Brown's video. I basically took this proof directly off of his channel. He has a really good animation for it, and he actually uses a concrete function to describe it.
Okay, cool.
All right, whenever you're ready.
Sorry, just 1 second.
Do not worry.
All right, perfect. Yeah.
All right. So the next rule we have to cover is the chain rule. I don't know why I put the product rule for positive integers. Should be up here. Before we go into the next one, I want to backtrack really quickly. Remember when we did the power rule, we showed that the derivative of x to the n is equal to n times x to the n minus 1?
Yep.
Remember, the values of n we were using were positive integers, 1, 2, 3, etc., right?
Yeah.
So this rule only works so far if our n value is an integer and positive.
Yep.
So right now, we would not know how to calculate the derivative of x to the pi power, right?
Correct.
Exactly. So I just want you to keep that in mind.
Okay.
Right? The only thing we know now is if x is a positive integer. So we could calculate the derivative of x to the 1,000th. It would be 1,000 times x to the 999. Juice WRLD, am I right?
Yes, sir.
That was a terrible joke, but you get what I'm saying. We can.
No, do not shame yourself. That was golden.
But yeah, so we can calculate the derivative of any x to the n as long as n is a positive integer. But just be careful because we can't do it for weird numbers yet. We will though tomorrow.
Okay, cool.
All right, the chain rule. So actually, I was thinking if you guys would be interested, I recorded a video on the chain rule for my math YouTube channel in April. It's called the chain rule in 4 minutes. It's very quick. And I think maybe it'll be faster and easier than explaining it, and it might be, more concise. So would you guys rather just me play that video and pause it when you guys have any questions? Because it's still me talking. It's just recorded video.
Okay, yeah, I'm fine with that. From when you played the Overwatch clip, when you play videos, it's like 3 or 4 frames per second.
Oh shit.
So like maybe if you like sent it to us and then because I'm still happy to watch it.
Yeah, so it's on.
A little hard to follow.
Yeah, do you guys know my math YouTube channel?
I don't think I do.
Okay, so go, Henry. You follow me on Instagram, right?
Yeah, I do.
Okay, so if you go to my Instagram, in my bio, there's a link to my math Instagram channel.
Okay, yeah.
And Instagram, and in my bio to my math Instagram is a link to my math YouTube channel.
I see it. Yeah, I follow your math Instagram too. Okay, cool. Here, I'm gonna subscribe actually right now.
All right, so you can watch that later, but I'll just do.
Man, you got 24 subscribers.
I know, right? And you know what's.
You,
Mr. Normanton, I'm the only person that he is subscribed to.
Wow,
yeah.
That is impressive.
Yeah, I know. I don't need women swarming me, so don't tell your friends.
Okay.
All right. So what I'll do is I'll just do a 4-minute version here live, and it won't take that long. And if you want to watch and if you want to watch the video in your own time, you can do that too. All right. So remember when we thought about derivatives with our machines, where we said if we have a machine function, a function that's represented as a machine, and it takes in a number x and spits out the output f of x. All right. The derivative at a certain endpoint. The derivative with a certain input is just whatever a tiny change to our function value is divided by a tiny change in our input. That relates to the graph example by saying, well, if we want to find the derivative, we take a tiny change to our y value and divide it by a tiny change to our x value. So the derivative with our machines is just a tiny change in our output divided by a tiny change in our input. Would you agree?
Yeah.
Cool. All right, am I good to clear this?
Yeah, I'm good with that.
So the chain rule tells us how to find the derivatives of functions like f of g of x, where you take one function and you stick it inside another. An example of this function would be sine of x squared. Do you see how x squared is stuck inside the sine function? This is an example of f of g of x, the composition of two functions. So if we go back to our machines, all right, it's clear to see that our function f is not taking in x's inputs anymore, but is rather taking in g of x's inputs and spitting out f of g of x's outputs. Right?
Yep.
Cool. And remember the equation from before that a tiny change to our output, dy, equals the derivative of our function times dx. And we know how this equation works, right?
Yep.
Cool. This is really important. So I could say, well, a tiny change to our output, f of g of x, equals, so wait, let me rewrite this. This tells us a tiny change to our output is equal to the derivative with respect to our input. You see how it's f prime of x?
Yeah.
This is because when we take, for example, when we take the derivative of x squared, we're asking what the slope is, and we say with respect to x, because the change in our input is x. So the slope we're evaluating is with respect to x, because x is our input.
Okay.
So when our input is different than x, in this case, our input is g of x, right?
Yep.
So so instead of saying the derivative with respect to x, I have to say the derivative with respect to g of x because our input is now g of x.
Okay.
Does that make sense?
That makes sense.
So basically what I can say is, well, if our output dy is equal to the derivative of our input times a tiny change to our input, that's what this equation is saying, right?
Yep.
The only thing we have to change for this example is what our input is, because our input is g of x. So df of g of x is equal to f prime, and instead of x as our inputs, we have g of x as our input, so we put g of x, all right, times dx. But instead of our input being x, it's g of x here, so we have to put times dg of x. Would you agree with that?
Wait, explain the last part why it's dg of x again.
Okay, let me maybe backtrack and explain the whole thing again because I think I have a better way to say it. This equation tells us that a tiny change in our output is equal to the derivative of our input, right? Because normally x is our input,
yep,
times a tiny change to our input, dx.
Okay.
So normally we're dealing with x as our inputs, but with this example, when we have f of g of x is the input going into the function, and our output is f of g of x. So we have a different input in this case.
Yeah.
So we write the same thing, except, well, we know that our inputs are no longer x, but rather g of x. So we just replace the x's with g of x's because that's our input now.
Okay.
Cool. So df of g of x, the tiny change to the output, is equal to f prime of our input, g of x, times dg of x, the tiny change to our input.
Okay. Yep.
Cool.
I understand that.
All right. So let me go to the next slide.
Ryan, are you good?
Ryan, you all set? I'll take that as a yes, but if not, just shout out at any time, okay?
I think he said yeah. Also, keep in mind we have 3 minutes before the
Okay, we're going to finish this rule by the end.
Okay, perfect. Just wanted to let you know.
Yep, thank you so much. All right, so so if we said that the change to a function dy equals equals the derivative of that function times dx, could you think of a way to rewrite this? If this is a tiny change to g of x, and we know that a tiny change to a function is equal to the derivative of that function times the change in its input, could we rewrite this as something else?
You could rewrite it as g prime of x dx.
Exactly. Perfect. And you feel comfortable with how that works?
I think so, yeah. I'm solid 89%.
Okay. Is there any? Do you have any idea what the 11% is confusing about? Because I could try and reiterate it.
I think with a lot of this, it's not fundamental. I'm not really understanding it. It's just there's a lot going on. So.
Yeah, that's fine. My goal isn't that you'll memorize these proofs. I don't want
just to show us so that we understand.
I just want you to be at every step of the way you go yep, that makes sense, that makes sense, that makes sense, that makes sense. So then you could look back and go I just did this proof. I might not remember exactly what it is, but I remember agreeing with it every step of the way. So now I can use the equation and know that it's valid. Even if I forget why it's valid, I know that I know that it's valid because I agreed with every step of the way. You know what I mean?
Dude, that. Sorry, this is a little off topic. That alone puts you ahead of so many teachers. That I'm so glad you're teaching it that way because that is that's the right way to teach math.
Yeah, exactly. Good. I appreciate it. It means a lot, by the way. You guys are doing great. All right. So we have this equals df, and if we cut out, I'll just come right back, okay? And then we'll finish, and then we'll talk in just a second, okay? If it does cut out. So we got df of g of x equals this, right? F prime of g of x times g prime of x dx. We agree with this equation from here. We said that the tiny change to f of g of x is equal to f prime of g of x times g prime of x dx, because we rewrote dg of x like this because you said it was valid, and I agree.
Yeah.
Cool. I'm going to divide both sides by dx. All right. So we have f. So this is just one term, right? We have f prime of g of x times g prime of x times dx. So if I divide this side by dx, we just get rid of the dx here. We're dividing dx by dx. Would you agree?
Yeah.
Cool. So tell me, what does this side say? What does this side mean?
That is the derivative of f of g of x.
And so then, what would we expect this to be? We would expect this to be the rule that tells us what the derivative of f of g of x is, right?
Yeah.
And lo and behold, it is. The derivative of f of g of x equals f prime of g of x